So our mathematician spotlight today is Moon Duchin. Moon is an associate professor at Tufts University, and she studies geometric group theory, geometric topology, and dynamical systems. And a couple years ago, Moon realized that there's this big problem, gerrymandering. Have you heard of it? And that she could study it and help with it with geometric group theory. And there's a short clip here I'd like to show you about it, because it does a good job. Are you ready? Okay.
Gerrymandering is generally the blanket term for abuses in redistricting. With the pen comes the power.
The Census Bureau releases data at the start of the decade showing how populations shift. That data is then used by lawmakers to redraw districting maps.
You stuff too many of your opponent's voters into too few districts so that they get fewer seats out. Cracking is where you take your opponent's voters and you disperse them over several districts rather than letting them be sufficiently concentrated into one. Well, there's this whole field called geometry where that's kind of what we do is we think about shape.
All right, so that's what Moon does. That's what she's working on, gerrymandering. I want to go back to this right here. Nope. This one right here. So this is Pennsylvania 7. These on the screen here are 3 of the worst examples of gerrymandering in the country. This one is in Chicago. This one I believe is in North Carolina. And this is Pennsylvania 7. So we live, see how this little bit is cut out here? This is Swarthmore College, right here. So here's what happened. And I have this nice map, this puzzle here with the congressional districts of Pennsylvania, which you can put together. They look kind of crazy. So here's Pennsylvania 7 in red, and you can see this little bit is cut out. We are living at Swarthmore College in Pennsylvania 1, which is the blue district. So some of these are kind of small, that's why I colored them in. Some of them are stuck together. So the blue district here is Pennsylvania 1, which includes Center City, Philadelphia. Now you know, generally cities are Democratic, and Swarthmore College also Democratic. So the Republicans who drew the lines wanted to connect Swarthmore to Center City, Philadelphia to pack all the Democrats into one district, so it would be overwhelmingly Democratic, and so that Pennsylvania 7 here, with all the Republicans in it, could have enough of a Republican majority to stay Republican. If they had taken this bit of Swarthmore and thrown it into Pennsylvania 7, it wouldn't have been enough Republican. Amazingly, so Pennsylvania has 18 representatives, and in the state there's a 5-to-4 ratio of registered Democrats to registered Republicans. So if it was sort of a 1-to-1 representative thing, so representatively you should have 10 Democrats and 8 Republicans, because registered it's at a 5-to-4 ratio. But because of the gerrymandering, what we actually have is we have 13 Republicans and 5 Democrats. So this is a big deal. So in this video clip that I showed you, they said that the Supreme Court was just looking at a case about Wisconsin. But this clip was made in October. Do you know which state is in the news right now this week? Yeah. Pennsylvania, yes. Yes, the Pennsylvania State Supreme Court argued that Pennsylvania's, I'm just repeating what you said, districts are illegal by the Pennsylvania State Constitution. They ruled that on Monday. It is now Friday. That was just 4 days ago, and gave the lawmakers until February 5th, which is not very far away, to redraw them. So hopefully this puzzle, which is here, is going to be an anachronism, and we're going to have less gerrymandered districts in the future. So this is what Moon is working on. I just saw her give a talk at a big math conference in San Diego. She talked about gerrymandering, how math can help with it, and how it's a social justice issue. And at the end of the talk, she got a standing ovation. Doesn't usually happen in a math talk. It's very unusual. So let's see. And I'm also wearing a shirt from some research that I did with Moon this past summer. So we'll just do that. OK, great. So thanks for watching a video clip. I don't usually show video clips, but I felt that that one was a pretty efficient way of showing both Moon and gerrymandering. Good. OK. Great. And it had a good soundtrack. OK, so let's see. Last time, we talked about multivariable functions. Functions from R2 to the plane, functions from R3 to R. Today, lest you think that all multivariable functions are functions of x, y, and z, rectangular coordinates, we're going to do other coordinate systems. So that's the plan. So today, new coordinates. In particular, cylindrical and spherical. So that's the plan. They work really well for round things. So x, y, z coordinates work great for planes, things that are flat, but they're not as easy to use for things like spheres. At the end of the day last time, we talked about how a sphere isn't a function, because for a given x, y point, you have two different z points. So it's not so good in rectangular coordinates, but we'll see that it's really great in spherical coordinates. It's easy to write down equations for spheres. So let's first do cylindrical coordinates. So cylindrical coordinates are r, theta, and z. So r, so if we make sort of a cylindrical graph paper, I'm going to draw, these are in perspective, some circles in the xy plane. And then we'll have our z-axis coming up. So this is like three-dimensional graph paper for cylindrical coordinates. So r is the distance from the z-axis. That's what r is. So if you have some point out here, you measure the distance of the z-axis, and you call that r. That's how it works. And then theta is the counterclockwise angle from the positive x-axis. So if I draw my x-axis here coming out, and I have my point here, maybe its shadow is there, theta is the counterclockwise angle that you have to go, starting at the positive x-axis, to get to your point. And then finally, z is, as usual, the height above the xy plane. And if z is negative, then the point is below the xy plane. So z is just this guy. There. Yeah. So we should play with these things. Let's do it. OK. So let's play with what we get if we just hold one fixed and let the others be anything. So for example, r equals 1. Now you might notice that cylindrical coordinates are basically just polar coordinates, but with z. It's like polar with z. So anytime you're working with polar coordinates, it helps to have a polar beverage just to like help you along, you know? OK, good. So while we're doing that, this will help us graph this. So let's draw our polar coordinate graph paper. Okay, so r equals 1. So we have 3 variables, r, theta, and z. So we're in 3 space. We have 1 constraint, so we expect a 2-dimensional thing. We expect some kind of surface. Does anybody have an idea what this r equals 1 would look like? You have an idea? Yeah. It's just a cylinder. Can you say why you think it's a cylinder?
It just says that you have to be r away from the z-axis, but it doesn't have a constraint in both the angle around, I guess, around the z-axis, or just the height.
Yeah, awesome. Yeah. This constrains you to say that you're always 1 unit away from the z-axis, but it doesn't constrain you in your angle. So your theta can be anything, or in fact, it has to be everything, has to take all the values, and your z can also be anything. So you go 1 unit out, you get a circle here, a circle of radius 1, but then your theta can be anything, so you go all the way around, and your z can be anything, so you go all the way up and down. Nice, very nice. Yeah, so we get a cylinder going up and down. And then it continues infinitely. So it's an infinite vertical cylinder. Yeah, nice. Great. Okay, so let's try fixing or setting equal to a certain value the next coordinates. So how about theta equals pi over 2? Let's graph that. So I'll make my cylindrical graph paper here. And I guess for this one, I'll need my x-axis. Okay, can anybody guess what this will look like? Yeah.
So I think it would be a plane.
A plane.
Extending like infinitely upward and then outward in the direction of pi over 2.
Yeah, nice. Yeah, it's a plane going infinitely upward and downward and then in the direction of pi over 2. Nice. Because what? Theta can be anything. Theta has to be fixed at pi over 2, but r can be anything. So we go to pi over 2. Maybe here's pi over 2. Pi over 2. R can be anything, so our line just extends out. And then z can be anything. So we go up and also down, because z can be negative also. So try to draw a picture. If you come late and you see the picture, you might not know what it shows, but if you see it being drawn, you can tell what it is. Yeah, question?
So only be on that side of the z-axis and extend on the other side?
This is a great point. Is it on both sides, or is it just this half plane going back? This yellow part, we get when r is less than 0, we get sort of a back half plane. The half plane going away from us that stops at the z-axis. But then if we let r be, sorry, that's r greater than 0. But if we let r be less than 0, we get the things on the front. So it's sort of like you go pi over 2, and you go r equals 2 or something, you get over here. You go pi over 2, you go r equals negative 2, you go backwards. So that would allow us to get everything over here, all this part. If we allow r less than 0, we get sort of the front half plane. And if we let r be anything, negative or positive, then we get this whole plane. And we usually let r be negative and positive, so we get the whole plane. Yeah?
I'm a little confused. So I thought r is essentially like the radius from the
Yes.
z-axis.
Yes.
So I thought that no matter which direction you're in, you could get like a positive r value, which is what I was thinking. I thought that the angle is the only thing that's like, you're just going 180 in the opposite.
That's right.
direction.
Right. So if I had my point here and I wanted to specify it, I'd probably use a positive r to specify it for sure. But what if you were given something like, hey, my point, it's at r equals negative 1 and theta equals pi over 2. Well, you just go, okay, theta equals pi over 2, I'm here. But now I'm not going r equals positive 1. Where should I go? Well, the only thing to do really is to go backwards. Say r is negative, goes in the opposite direction. That's the convention that we use for a negative r.
Okay.
Yeah.
And so if we had an angle that was 100 degrees, 80 degrees opposite, then the directionality of r flips. Am I getting that?
That's right. If you add 180 degrees to your angle, you switch the sign of r. Exactly. Yep. So you can always use a positive r if you feel like it, but if you're given a negative r, this is how you interpret it. Yeah.
So normally when we write r can be anything, we don't include negatives, right?
Normally in polar coordinates, we let r be positive or negative. We let it to be anything. So I think we would say for this, we could say, assuming r less than 0 is okay, we get a whole plane. And usually the convention is that we do let r be less than 0. So, yeah. But this is exactly the right conversation to have, because r negative, clearly a little bit confusing when we think about it as a distance. Distance is usually taken to be positive. Yeah. Okay, and let's do one more. Let's fix z. So let's do z equals -2. So I'll draw my polar graph paper here. Anyone have an idea what this should look like? Yeah, you do?
It's circle centered at c.
Yeah, an infinite circle. So here's -2. Can you say a little bit more what you mean about an infinite circle?
So because x and theta, I mean r and theta can be anything.
Yeah, right. R can be anything. Theta can be anything. Okay, good.
So that has to be centered around c. So raising something outward.
Yeah, nice. It would be an infinite number of rays, because it's a ray, because r can be anything. So we all get all these rays. And then theta can be anything, so we have all the rays going around. Yeah, nice. So we sort of get all the rays coming out. Can you see what the collection of all those rays or all those circles would look like? Yeah? Just a plane, yeah. Yeah, you can think of them as circles, all the circles going out or all the rays going around. And they actually turn out to be this whole plane down here at z equals -2. Nice. So we get all these rays or all these infinite number of circles coming out, and they give us the whole plane down there. Nice. So this turns out to be a plane, horizontal plane. Yeah. Great. Okay. So the idea of that was to look at each variable separately and see sort of what it does. But we should probably try putting them together. So let's try an equation that puts them both together. So how about z equals 2r? Okay, so again, we have 3 variables. We're in 3 space, but we have 1 equation. So we expect it to be some kind of surface. Since z equals 2r, z and r are constrained. But theta can be anything, because it's not in our equation. So it takes on every value. So what I recommend for things like this is to draw it from the side, like a side view, and then spin it later, because theta can be anything. So let's draw it. We have r here and z here. And the idea of this r is that this is the xy plane from the side. So I've actually drawn all of 3 space here, but this is my xy plane just from the side. So this r represents the xy plane in a side view. Yeah? Okay. So let's just draw z equals 2r. Well, z is like the y coordinate and r is like the x coordinate. So this is just like y equals 2x. So it's some line here. So you think about it sort of like y equals 2x. And then theta can be anything. So spin it around, exactly. Yeah, exactly. So we spin it around. So here we go, spinning it around. We take this point and just sort of spin it around like that. And we get this shape, this cone. Yeah, so it's a cone. So it's a, or you might call it an infinite cone. And it has the part going up when r is greater than 0, and then also the part going down when r is less than 0. Yeah, this part is for r less than 0, this part is for r greater than 0.
Where's that z?
Well, z is 2r. So it's r greater than 0 and z equals 0 up here, and it's r less than 0 and z less than 0 down here. Yeah. Great. Great. Yeah, questions or ideas? Yeah.
So then is there a way to like draw this, convert it to the x, y, z plane?
Yes. We can. The equation?
No, like to, instead of having the ZR plane, convert it onto the XYZ plane.
Oh, in 3 space?
Yeah.
Oh, I guess I sort of did that here when I spun it. So if this, we could call this we could say, okay, this was a side view, but now this is going to be my x-axis, and now I'll draw my y-axis going back. Ta-da! Now I'm in 3 space. Yeah. Yeah. Yeah, good question. Okay. Okay, so that's one that relates to variables. And now let's just try one more. Okay, so let's try to graph the surface represented by r equals 1 plus cosine of theta. So r is 1 plus cosine of theta. Z isn't in the equation, so z can be anything. So maybe the best thing to do is just draw this in the plane and then know that we're going to get a cylinder over whatever we get. So just like here, we drew a circle, r equals 1, and then we said z equals anything, so we went up and down. Here we'll figure out what picture we get in the xy plane, and then just say we get a vertical line over everything. So let's draw this here. Okay. We'll plot things here. So the plan is going to be, let's plug in some different thetas. So for instance, here's theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2. Those are the axes. And then maybe try some other values like theta equals pi over 3, and 2 pi over 3, and 4 pi over 3, and 5 pi over 3, okay? And we'll figure out what the radius is at each of these places, and we'll plot those points on the graph, and then somehow figure out how to connect them in a nice smooth way. That's the dream. If I just looked at this equation, I would not know what it looked like. I would have to plot the points. So I would make myself a little table, so that's what we're going to do. Because I'm running the show, so if I need a table, we get a table. Okay, so the thetas we're going to try are 0, pi over 3, pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, 5 pi over 3, and pi. Gosh, that's a lot. Okay, and now if we wanted to do 1 plus cos theta, it's an awful lot of work to do that in one step. So I recommend computing cos theta and then adding 1 so that you don't make any mistakes, or so that they're easier to find. So cosine of 0, you have a helpful unit circle right here that you can use. Cosine of 0 is the x value of a point with theta equals 0, so it's 1. Cosine of pi over 3 is a half. Cosine of pi over 2 is 0. Negative and then negative a half. Then negative 1, negative a half, 0, 1 half, and 1. Okay? And now let's add 1 to all of those. So we get 2, 1 and a half, 1, a half, 0, a half, 1, 1 and a half, and 2. Okay, so now we're ready to graph things. So at theta equals 0, now this is r here. R equals 1 plus cos theta. So at theta equals 0, our radius is 2. So if this is I've made this so that this is a circle of radius 1, and this is this is a circle of radius 2, and this is a circle of radius 1. That's the idea. So at theta equals 0, our radius is 2. At theta equals pi over 3, our radius is 1.5. At theta equals pi over 2, our radius is 1. at theta equals 2 pi over 3, our radius is 1/2. And then at theta equals pi, our radius is 0. So the idea is you just sort of sweep around and you figure out where you are. If you wanted to be very precise and careful about this, you could add in some other variable, some other angles of theta that you can compute, like pi over 4 or pi over 6, that sort of thing, to make it super accurate. Okay, and then going down at the bottom, for 4 pi over 3, our radius is 1/2. And then for 3 pi over 2, our radius is 1. And then for 5 pi over 3, our radius is 1.5. And then for 2 pi, it is 2 again. Okay, so it looks like we have enough points to make a nice picture here. We don't need to go back and make any more. So let's do it. So it looks something like that. So it starts out at 2, and the radius decreases all the way down to 0, and then it increases back to 2 again. So we get this nice shape. And people think this looks like a heart shape, so this kind of shape is called a cardioid. Should you ever need to refer to it again, you can call it a cardioid. Okay. So that's the picture. Oh, man, I didn't even drink my extra super juice for drawing polar things. But if we want to draw it in 3 space, it will be a bit tricky. So you kind of have to plan what you're going to do before it starts. Huh? Oh, that's exciting. It's been going for a while. All right, at this point, I think we're done with this. Good. Sorry, guys. Okay. Good. So let's draw it in 3 space. So in the xy plane, we have this nice cardioid shape. And then you imagine taking this shape and sort of like a cookie cutter, picking it up and just sort of sliding it up and down in space, whatever that looks like. So there's a sort of a cusp here. And then this sort of goes up. So you can imagine, oh yeah, this goes up too. So, yeah. Okay, so it looks something like that, this cookie cutter heart shape, and then it extends infinitely up and down. This would be quite difficult. Oh no. All right, let's plus the button over here that says that things should shut off. Okay. Okay, so this would be quite difficult to specify in 3 coordinate, in x, y, and z, but it's easy in cylindrical. Okay. Questions, ideas? Okay, so cylindrical coordinates, good for cylinders. How about spherical coordinates? Okay, so the idea is to have lots of tools in your pocket, and we want you to have rectangular coordinates, cylindrical coordinates, and spherical coordinates in your pocket whenever you might need them. So, spherical coordinates. So spherical coordinates are rho, phi, and theta. So let's see, this rho is the Greek letter rho, A-R-H-O. This guy is phi, P-H-I, and then that's our usual theta. By the way, this is a rho. It's the Greek letter for R. It's not a P. So if you ever make this letter, which you will, start at the bottom and then go up, and then go around like that. That's how you make a row. It's a radius, so it's row. And in English, often when you use this letter in like sorority or fraternity names, you call it phi. But mathematicians have adopted the British pronunciation, which is phi. So we'll call it phi. Just one more logistical thing to say is that the order of these things is just a matter of convention. So in mathematics, we usually do rho, phi, theta. But in physics, they often go rho, theta, phi. So we'll be specific anytime we write down something just in coordinates like this. We'll say rho, phi, theta equals something, 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 just so you know which one is which. You don't have to memorize. It's all good. OK, and for phi, there are two different ways to make a phi. There's this way, and there's this way. And they're both the same. Sort of like when you make an A like this, and your friend makes an A like that, and they're the same thing. They're just a different way of making the same letter. Those are all the same. OK, enough logistics. Let's see what they will do for us. So rho is the distance from the origin. That's what rho is. So in spherical coordinates, you have your sphere. Maybe you have your x-axis coming out, your z-axis going up. And you have some point here that you want to specify. I want to say where, this one actually is a p. My point here that I want to specify. Well, the first thing that I do is I say how far it is from the origin. So this distance here, the distance is rho. OK, then the next thing that I want to specify is its angle down from the z-axis, or the North Pole. So the next thing I specify is this angle, which is phi. So this is the angle down from the z-axis. That's rho. It's very much like latitude, except that latitude is measured north and south of the equator, and phi is just measured down from the North Pole. So it's the same idea, but a slightly different measuring system. And then finally, theta is the same as theta in cylindrical coordinates. It is your distance counterclockwise angle from the x-axis. So if I were to find the shadow of p here in the xy plane, then this counterclockwise angle is theta. So it's the counterclockwise angle from the positive x-axis. So that's what it is. So these allow us to uniquely specify a point in 3 space. Oh yeah, and theta is very much like longitude. You have to pick an arbitrary place to start it. We arbitrarily choose to start measuring at the x-axis, just like with longitude on the globe and the Earth, we arbitrarily decide that 0 is Greenwich, England. Yeah, OK. So let's do the same thing with graphing the surfaces when we hold one of them constant and vary the others. So let's graph what we get when rho equals 2. Can anybody see what you would get? Yeah.
Would that be a sphere?
A sphere, yeah. Why would it be a sphere?
Because like you know the distance from like the origin, but like everything else is like anything. So it would just be like a sphere, I guess.
Yeah, nice. Yeah, you know the distance from the origin is fixed at 2. So you just say my distance from the origin is 2. Sounds like a sphere to me. Also, she pointed out that phi can be anything, and also theta is anything. So you have your radius, and then you can just go in any direction you want. Good. So you get a sphere of radius 2 centered at the origin. Nice. Very nice. OK. The next thing we can fix is phi. So how about phi equals pi over 4? Can you imagine what that would look like? Yeah. Yeah, exactly. It's like a cone that extends outward infinitely because you know that your angle down from the z-axis is pi over 4. And then your radius can be anything, and your theta can be anything. So you get the whole cone. Very nice. Great. So we know here's our z-axis. We know that our angle here is pi over 4. And then we just spin it. So we get this infinite cone. And usually in spherical coordinates, rho is taken to be positive. So the convention is that here rho is usually taken to be positive. So we would only get the top nap of the cone. Yeah?
You said that phi is pi over 4.
Yep.
So why are we including the negative pi over 4?
We are so phi is pi over 4, but theta can be anything. So theta takes us all the way around. So when we did phi equals pi over 4, maybe we think of just we only get this ray here, but then we spin it all around for all of our thetas. Yeah. Okay, and finally, let's try theta equals 1. And we'll measure this in radians. So 1 is like around 57 degrees. So if we draw our spherical graph paper here, oops. Always draw the circle first. Here we have our x-axis coming out towards us, maybe, and maybe our y-axis back there. Can anybody see what this would look like? Yeah. Yeah, exactly. It would just be a plane that extends 57 degrees counterclockwise from the x. Yeah. So we could plot 57 degrees is like a little more than halfway from x to y. Here's theta is 1 or 57 degrees. And then let's see, z can be anything. And rho can be, rho can be anything. No, wait a second. What angles do we have here? Yeah. Phi can be anything, and rho can be anything. So since rho can be anything, we get this as long as we want it. And then since phi can be anything, we rotate this guy up and down. So we get this whole plane all the way up and down. So this is a half plane at theta is 1. So this really is just half the plane going away. Yeah, nice. Questions or ideas?
And it can never be the full plane.
This one, let's see. It can never be the full plane. Let's check. So theta makes sure that we're going at this 57 degree angle. Phi can be anything, so we can go up and down. Oh yeah, phi. That's a great question. That's a great thing. Phi is usually taken to be between 0 and pi. So our convention is that rho is greater than 0, and phi is between 0 and pi. So we start at the top, at the North Pole, and we go down to the South Pole, but we don't go further.
Okay, it's just because of the conventions.
It's because of the conventions that restrict things to certain ranges that we can't go all the way around. Yeah. All right. Good question. Okay, so let's just do one more graphing with this. So let's graph rho equals 2a cosine phi. Okay. 2a cosine phi? 2a cosine phi. So once again, so let's see, this has rho in it and phi in it, but no theta. So theta can be anything. So maybe the thing to do is to draw it in the xz plane and then spin it. So we'll draw this thing in the here's like a side view of the xy plane. And here's our z. Okay. And rho is 2a cos theta. We're letting a be just some variable. So maybe this is a circle of radius a and a circle of radius 2a. And again, we want to plot some points and graph them and see what they look like. So let's make ourselves a chart. So we have phi, cos phi, and 2a cos phi. And I think since, yeah, it will be enough for phi to go from, let's see, 0 to pi. That's what we should do. Aha. Okay. Okay, so phi. We should start it at 0 and go to pi. So let's try all these. So here at the top, phi is 0. Then phi is pi over 6. Phi is pi over 4. Phi is pi over 3. Here, phi is pi over 2. Here, phi is some other things. Gosh, what should that be? For the, what? So we're starting at the, so we're measuring from the top.
Measuring from 0, that's the 0.
This is here 0, pi over 6, pi over 4, pi over 3, pi over 2. And then we get some more numbers. Let's see. Here, phi is pi. 2 pi over 3? Great. This one? 3 pi over 4? I think. This one? 5 pi over 6? Okay, so let's try to get all these values. So if phi is 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Okay, well, let's see what we get here. Who knows how things will go? So if theta equals 0, if phi equals 0, cosine of phi is 1. Yeah, nice, okay? If phi is pi over 6, I think cosine is root 3 over 2. So we get root 3 over 2. Pi over 4, we get root 2 over 2. Pi over 3, 1/2. 1/2? Good, 1/2. Pi over 2, we get 0. Okay, 2 pi over 3. Let's see. Cosine of 2 pi over 3. It's on the left side. I think these are going to be negative. It's minus?
Minus half. Yeah.
Minus 1/2. Okay. So I think we can stop doing them now because this is our radius, and our radius has to be positive. So these guys are all going to be negative, so I think we do not have to do them. So these are going to be negative, and we want a positive row, only a positive row. So we do not have to do these. It turns out our picture is going to be all up here. Okay, good to know. So let's try to fill these in. So then rho is 2a cos phi. So 1 times 2a is 2a, and then root 3 over 2 times 2a is root 3a, and then root 2a, and then a, and then 0. Okay, so that's everything that we need. Okay, does anybody know what root 3 is approximately? So we can graph it?
1.7.
Yeah, about 1.7. So this is around 1.7a, and how about root 2?
1.4.
Yeah, 1.4, okay, about 1.4a. Okay, so now let's try to graph this. So we know that at phi equals 0, up here at the top, rho is 2a. So this outer circle is 2a, so we're up here. Then, when phi is pi over 6, our radius is 1.7a. So here we're at 1.7a, then about 1.4a, then 1a, and then 0. Okay, so I'll connect those. Okay, and now theta can be anything. So we take our picture and we spin it. So we get something round. What do you think?
Looks like an egg.
Looks like an egg. Yeah. It turns out it's a sphere. So my picture, who knows, if you draw a picture that's maybe a little bit not so accurate, it might be a little bit lumpy. But you could guess maybe it's a sphere, maybe it's an egg shape. It turns out it's a sphere. So it turns out it's a sphere of radius, well, let's see, if this whole but is 2a, then this is a, radius a, centered at this point, so a above the origin, so we could call it, we could say it's centered at the point x, y, z equals 0, 0, 2, just to be clear about what coordinate system we're using. Or we could call it rho phi theta equals, let's see, sorry, not 2, that would be a. Rho phi theta would be, let's see, distance away is a, phi is 0, and theta is actually anything, it doesn't matter. But I don't know, let's say 0. Yeah, question?
Can you talk again about why we can't have a negative radius? There, I guess it looks like the negative radius would just be the other side of the circle.
Yeah, sure. So our convention in spherical coordinates is to take rho always positive.
Okay.
Yeah, if we allowed it to be negative, then we would get the other side of the circle. Yeah, right. If we had kept going here, we would have gone one out, but with a negative radius, and we would have gotten right here. So if we had allowed negative radii, we would have just gotten these other points on the other side. Good point. Yeah. So it wouldn't ruin anything. It's just to keep things easier for ourselves. Okay, great. And then the last thing to do is to go back and forth between spherical and rectangular coordinates. In the interest of time, you may have seen that to go back and forth with polar coordinates and rectangular coordinates, x is r times cosine of theta, and y is r times sine of theta. And since we just keep z the same, this is how to go back and forth from cylindrical to rectangular. Okay, perhaps so. There's that. And then how about to go from spherical to rectangular? This one is more interesting, so this is the one that we'll focus on. So you're given rho, phi, and theta, and you want to figure out what are x, y, and z. So we want, in the end, to get x, y, and z. It turns out, just like in cylindrical, the easiest one to get is z, but it's a little bit more tricky than just writing down z. So let's use this picture again. So here's our point P, whose coordinates we want to specify. We know the angle down from the z-axis is phi, and we'd like to know, first of all, what is the height, z, up to this point? And we know that the radius away from the origin is rho. So the clever thing to do is to just drop this perpendicular and find the shadow of the point P in the xy plane, and then use this vertical right triangle here. And since this angle is phi, by opposite interior angles, we know that this angle up here is also phi. Or if you did not want to do that, you can create a rectangle and say this length is also z, and now I have this little right triangle. So using this yellow right triangle here, which I'll pull out, z is with the long leg, in this case. Here's rho, and the angle at the top is phi. So we can get z. Z is just rho times cosine of phi. So z here is rho times cosine of phi. So rho cos phi. Now the next thing that we really want is x and y. So here are x and y. So if I make a little triangle here, this distance is the x, and here is the y. And so I'll pull that little triangle out here. Here's x and y. And then the hypotenuse is r. It's what we called r in polar coordinates. So it's actually in this yellow triangle here. So we can get r. R is rho sine phi. So we can put that rho sine phi in here. Rho sine phi is the hypotenuse of that little triangle in the xy plane. And now x is hypotenuse. Let's see, where's theta? Theta is here. So x is hypotenuse times cosine of phi. So x is rho sine phi, that's hypotenuse, times cosine of theta. And then similarly, y is hypotenuse, rho sine phi, times sine of theta. So the idea is you use these two cleverly chosen right triangles in order to get your coordinates back to rectangular. Okay, thank you everyone. I will post homework for you and see you on Monday.